I'm Jan Vitek, and I would like to welcome you to my talk entitled Data Scientists Are Programmers Too. In this talk, I will be talking about data science, and it bears to have a definition of the term. I put mine to the work of John Tukey in the 1960s, who wrote a very influential book entitled Exploratory Data Analysis. And in the book, he was arguing for a combination of statistics and computing to enable rapid exploration of experimental data. He was working at Bell Labs at the time, and his ideas were the inspiration for John Chambers to start the S programming language, which in turn became known as R around 95. The actual term data science, though, was likely coined by my Purdue colleague, Bill Cleveland, who came from Bell Labs and wrote a paper that argued that a new discipline, a new science was needed, one that would be rooted in statistics, for he's a statistician, but would combine computing technology with a very strong focus on applications. And this is probably the best definition we have of what data science is. Now, in practice, data science is about building data analysis pipelines, visualizing data, giving insights for decision makers. And what I would like to do is give you a little bit of an example of how one builds such a data analysis pipeline. What I'll do is I will start with something that is well known, the passenger list of the Titanic. We will try to predict who will survive, and I will do this using the R programming language and the dplyr package. So any data science project, here I'm using the R IDE and I'm building a notebook which allows me to mix computation and its results. Any data analysis project starts with data acquisition. Data acquisition is gathering the data from a source. Here we're just going to read it from a CSV file on disk, and you can see there's a table that comes with different columns. Many of these columns I will not need, so the first step in the pipeline will be to jettison the columns that I don't need. Then the first column survived was a double. I don't need floating points for this, I'll turn it into a factor. And the next step is, since 1 and 0 is not very sort of necessarily clear, I'm going to replace it by yes and no. All right, and actually here I flipped yes and no, so I'm going to correct myself. Then what we can see by looking at the data is that each passenger's name has a title embedded between a comma and a period. These titles are handy, so we will synthesize a new column. You see this at the end of the table under the name title, and the title is extracted with a regular expression from names. We'll turn it into a factor, and then, since there is some redundancy, we'll collapse multiple identical titles into a smaller set. Now we're ready to do some more data analysis. We're going to look for missing observations. And this visualizes them, showing that the H column has 177 missing observations. This is probably too much, so we need to fix this. And to fix this, we are going to group the data frame by title and then impute missing observation with the median of their title class. Now we have a new data frame, and this data frame allows us to do some visualization. So for instance, we can visualize survival by title. And the bar graph here will show the last bar is men, and you can see men have a lower survival rate than women and children, which is probably as it should be. Now the next graph we're going to plot is survival as a function of your ticket price. And here we'll give you a density plot. And you can see this pink peak at the beginning suggests that cheap tickets lead to bad outcomes. All right, so at this point, let's say we have explored the data set enough, and we will now create a model. Here I'm using random forest, and I'm building a model for survival, predicting survival as a factor of age, ticket price, and title. And here I need to rerun the notebook because I had deleted a column that I need, and I can look at the model. At the bottom you see the accuracy was 85%. All right, so what have we done? Well, to summarize, we have written a 15-line R program that embodies this data analysis pipeline, and this program is predicting survival of passengers for this particular data set at 85% accuracy. What could go wrong? Well, this is a program after all. And like any program, it is possible we made mistakes. When I recorded this animation, I've momentarily swapped the meaning of survived and deceased. Had zeros and ones in the wrong places. It's a very easy mistake to make, and there is nothing that would catch this, other than maybe looking at the result and finding something funny. But you know, it's not even always, it's certainly not always the case that you could spot such mistakes by just eyeballing the final results. So how often do mistakes happen? Well, we asked ourselves that question, and Helena Kothaus and myself, we did a preliminary survey in 2019. We sort of asked about 58 academics, 27 industrial respondents, what kind of errors they made during various stages of the data science process. Just for the record, there were the respondents were mostly evenly split between R and Python users. So if we think of the 6 stages of data science as being problem formulation, data acquisition, data cleaning, data exploration, data modeling, and reporting, our respondents found various potential problems at each stage. You know, formulation is more a specification requirements problem, so you can have communication issues, you can ask the wrong questions. The cleaning process, typically you need to handle outlier, missing values, and you may have type conversions and so on. So what we were wondering was, how often do these problems happen? And the answer that we were able to elicit was in the form of this graph, which I'm showing now, which shows for each stage and the 2 kinds of participants, the percentage of respondents who encountered a problem in one of their projects at that stage. So to read this, for instance, we can take the acquisition stage, and there you'll see that academics have about 28% errors, so that is 28% of our academics had an error in at least one of their projects, and industrials 37%. So what can we take away from this graph? First, that the early stages are more error prone than the later stages, and then that there are two interesting discrepancies. One is at the formulation stage, where industrial respondents had way more errors than academics, and this is likely due to the fact that they have to deal with customers who are not always expert at formulating their problems clearly. On the other hand, the modeling stage, so that trend reversed, where academics encountered way more errors than industrial respondents. And there, the potential explanation we found is interesting. The industrial partners list, when we asked them which modeling techniques they use, had a very short list of mostly textbook techniques, linear regression, random forest, and a few others. And these are well understood techniques that probably they use on a daily basis, so they're familiar with those. On the other hand, our academic respondents, they came up with a very long list of techniques, and many of them were cutting edge. And it is not unreasonable to assume that these are not as well understood and easier to misuse. But if we take one more step back and we look at this, one thing that stands out is no stage is error-free, and thus, there is a likelihood that any data science project will fall to errors at one or more of those stages. So some of those stages are slightly out of the realm of computing. So for instance, formulation is more about communication, maybe requirements gathering, so it would be maybe more in software engineering. But many of these stages, most of them, are tied to steps of programming. And we know that programming is error-prone, so it is not surprising that we'll find errors in data science codes. So my research is going to be about how can we improve the work of practicing data scientists. To help data scientists improve, what we need to do is, well, use our expertise in programming languages and offer them better tools, better languages, better error checkers, better methodologies. And here we have a choice. We can either try an approach where we rethink the whole process and start from scratch, design languages that are targeting the domain, but designed for correctness. But there's a big but with that approach. It means losing all the investment in the existing infrastructures. The other approach is to take the existing infrastructures and try to evolve them without losing all the investment. And this is tricky because we want to make changes so that people have an easier time getting their data analysis right, without breaking with all the libraries and all the code that people rely on. We have an ERC grant at FIT in the Programming Research Lab, and that ERC grant is titled LA for Evolving Language Ecosystems, and this is exactly what it's focused on. The idea here is if we take the R programming language, or we could take Python, but we picked R. If we take R is not just a language. So here I'm showing that little piece, which is the core implementation of R, which tells me, how to go from one statement to the next. But it is also the core libraries. And we can say maybe the language implementation has maybe 100 people who have worked on it over the years. The core libraries, which include statistics, vector operations, operating system access, everything you need to do anything useful in R, there's probably 1,000 people who have worked on it. On top of that is where the real added value lies, the contributed libraries. In the case of R, there is a repository called CRAN. It's a curated repository that holds over 18,000 packages. And these packages range from statistical methods all the way to visualization techniques. And we could guess maybe that 18,000 packages have been contributed by, say, 100,000 people over the last 20 years. And on top of that, you have all of the user code, all of the notebooks, all of the internal uses of R, and all of the documentation. And by some metrics, this is used by tens of millions of people. So this is an ecosystem. And now when we consider making a change, say to the language, we have to very carefully study what impact it will have in the layers above it. Any breaking chance will ripple and will start breaking, libraries, packages, documentation. And the more you break, the less value there is in the whole ecosystem. So that's the challenge we're facing. So for the remainder of my talk, what I want to do is give you 3 example problems that we are studying and maybe sketch what we've done without going into much detail. The goal here being to show that programming language techniques have a bearing on data science. The first problem we want to address is what I call documentation drift. And this is a problem that is affecting the top layer of this ecosystem. Documentation comes in many forms. One of the sort of slightly less usual forms is forums like Stack Overflow. These forums gather question and answer threads that have practical examples of how to do things that are done commonly, and they come with a lot of embedded knowledge that is, reused daily by a very large community of practitioners. So, for instance, here I'm showing you a Stack Overflow page that's asking a question related to the Titanic dataset. It's using a version of dplyr. And what is interesting is this question was written 3 years ago, and it thus uses an old version of dplyr, which may or may not have been deprecated. It's hard to tell just looking at the question. So using that question ourselves may work or not, depending on whether the code is still valid. There are over 391,000 questions on Stack Overflow. So the research question here is, can we avoid them bit rotting over time? And I'll make this more specific. Can we take the code snippets that are embedded in these questions and migrate them to newer versions of the APIs? So here is a code snippet taken from this question. It uses dplyr version 0.6. And here is the modern equivalent in dplyr 1.0. These are not that different, really. So porting one to the other is merely a matter of removing some variables that are not needed and adding the pipe operation that connects the output of one instruction to the input of the other. This new code is slightly more efficient. It uses fewer temporary variables and is easier to read. So what we need to do is automatically find a rewrite that goes from old code to new code. And what we think to do in this space is to leverage GitHub. So GitHub has a wealth of projects and their entire histories. So it is not unreasonable to expect that for common programming idioms, there will be a piece of code somewhere that used the old API and was migrated in one or more steps to the new API. And our job is to find those migration examples, and from a set of examples synthesize a rewrite rule and apply it on our concrete target. So that's the goal. But it is often the case in science that things don't go as planned. So in this case, we were planning to work on this synthesis problem, and instead we ended up doing research on something that we needed as a prerequisite, and this is the ability to query GitHub. So GitHub is a wonderful resource, but it's a bit about like this proverbial needle in the haystack. It is way too big, and each project has long histories and forks and branches, and finding what we're looking for may be tricky. So what we decided to do is build an infrastructure for querying GitHub. And here's, for instance, an example. So the infrastructure is called CodeDJ. And here's an example query which looks at all GitHub projects, groups them by language, and then within a language selects projects that have at least 2 developers, and for which half of the developers have 2 or more years of experience developing. And we've chosen to write our query language in our infrastructure in Rust. This is an experiment. We were interested in the expressivity and trade-offs that this involves. And the infrastructure itself looks sort of like this picture here. So we have a system that composed of two components. One is called Parasite, and Parasite is a data store that continuously updates information from GitHub. And what it gets from GitHub is source code and metadata and commits, which is part of the metadata. And what is key for Parasite is to be space efficient and to be able to acquire data at a sufficiently high rate, given the fact that GitHub is throttling access to its APIs. On the other side, we have Django, which is a database that has a query language, which I showed you in the previous slide. So the way we use the system is when you want to do a query, we instantiate a Django database for that query, and then we run your query in it. One of the interesting bits about the system is that it was built to be reproducible. And by that, what I mean is every time somebody submits a query to Django, we archive it and we give them a receipt. And with that receipt, any researcher, so if you publish it part of your paper, any researcher can come to our database and use the receipt to run the exact query that was run in the exact information environment that we had. So the same state of Parasite, the same state of Django, which means everything in our system has to be timestamped, so that we can reset ourselves to a moment in the past. And of course, running the same query and getting the same results is reassuring, but what you can do also is do what-if experiments saying, well, what if you had asked that question back then? This work is being done by people in Prague, Konrad, Peter, and Alex, and it's currently under submission. The next problem that we find with R, and I think the same holds for Python, is that scripts mostly often just run. And even if something goes wrong, what will happen is you'll get a result, which may not be the result you want, but the script has run successfully. And this comes from the fact that R is very forgiving. It does a lot of conversions. Basically, most operations work with any data type, and there's a lot of effort that went into keeping computation running no matter what. Now, the downside of that is if an error creeps in, that error is likely to be masked, and you may not notice. So, what can we do? Well, one thought that we've had is maybe we should add types. So here, this example here from our Titanic dataset is the line that was mutating the survived column, and this line used strings to represent the old values of the survived column, zeros and ones, yet in the dataset these come as doubles. So implicitly here there is a type mismatch, which R can deal with, but you say one type mismatch, another type mismatch, and before you know it, you're computing over random values. Right. So types. Well, adding types to R would help us catch mismatches like this one, but it's difficult. It's difficult because R has millions of lines of code in the libraries in its core that have no type annotation. So we would have to, if we wanted a type system, we would have to annotate those. Interestingly, R is lazy programming language. So what that means is the calling convention in R is similar to Haskell, where when you call a function, the arguments passed to that function are bundled in a promise and only evaluated if you actually need them. And while this seems unrelated, it turns out that it has interesting interference with a type system. And lastly, R is very dynamic. You can call eval to create new code. You can introspect over pretty much any component of the language. And this also adds challenges for a static type system. So how do we proceed from here? Well, I said, can we type R? And I'll quickly kill off any hope of doing that. It's neither possible nor desirable. By that I mean turning R from what it is today to a statically typed language would be massively disruptive to the ecosystem. It would force all users to learn something new and all code to be adapted. This is simply not possible. So what we're thinking is can we find a way to type R gradually? That is, maybe start with the libraries. And for instance, here you see a function f which starts with no type annotation, and we could evolve it in some cases with, for instance, this question mark annotation that says, well, we're not entirely sure, but we think that x is of type data frame. But this is a weak indication. You shouldn't get too upset if that is not the case. And the stronger annotation, double column, which says definitely we insist that x is an array of integers. So these are possible elements of a type language. And in the past, in our previous work, all the way back to 2010 in a collaboration with IBM, we showed that it is possible to extend an object-oriented language with these types. We call them like types and concrete types. And the interesting property was that the more concrete types you add, the faster your code goes. Okay, so this sounds good, but, there is a but. The but here is that a key to getting the performance was that when we had concrete type annotation, it was possible to check the tag of the value as it entered the function. This doesn't work in R. It doesn't work in R because R is a lazy language, and when you get an argument, you don't know what it is. You don't know what it is until you can actually, until the function actually evaluates it, if it does. So, so what else can we do? Well, one idea would be, well, just since R delays the computation, we could also delay the type checking. Say, okay, residualize the type check and just remember that you promised to be of a type int, and if and when you get evaluated, perform the check, and if it's not an int array, throw an exception. That's completely possible, and some languages are actually using this strategy. The problem is that in 2016 we did empirical evaluation that showed that these delayed type checks have the unfortunate property that, generally speaking, the more you add types, the slower your programs go. And what I mean by slower, in the cases we measured, we could get over 1,000 times slower programs. So this is not acceptable for a language like R, which is already slow to start with. All right, so that doesn't work. What can we do? So one thought experiment would be, what about removing laziness, switching R from a lazy to an eager language? So what we did is we did a big corpus study. We looked at thousands of R packages to try to find out whether laziness was actually needed. And the bars on the top here show for each argument position of a function, how often do we actually evaluate it? And 86% are always evaluated. So these are clearly arguments for which laziness brings no benefits. There's only 6 that are evaluated sometimes, in some path yes, some path no. So what that tells us is that there is some evidence suggesting that R may not need laziness. Unfortunately, there are cases where you do need it, and we studied the code, we studied the large corpus we had in front of us, and we found that 0.5% of the uses of laziness end up meta-programmed. By that, it's a little bit in sort of a digression, but in R, when you receive an unevaluated argument, you can retrieve its source code, and then that source code can be used. For instance, you can modify it to evaluate it in a different environment. So this is called meta-programming, and 0.5% of the R code does meta-programming. Why did they do this? They want to extend the programming language, write a little DSL, all on top of R. So for these uses, we still need laziness. What we came up with was this idea that we would have a tool that would find which function needed to be lazy, keep laziness for those, everything else becomes eager by default. So we have published this at Uppsala in 2019. And last year we went one step further, saying, well, assuming we had a mostly eager version of R, what types should we give to programs? And here our idea is types would be expressed as comments, structured comments that can be used by tools, extracted, processed in any which way. And the question we were asking ourselves was, what type annotation, what type language to use, and also how do we type all the libraries that are out there. So we published a paper that performed type inference for function signatures. The idea was just, can we figure out what types arguments and return values of library functions are? And for this exercise, we picked the simplest type language we could come up with, the one that would be the most easy for our developers to accept. And I will show you now some example type signatures that we inferred. So these are 10 popular library function, and you can see their type signatures. So for instance, if I take the first line, the group indices function from dplyr, it takes one argument of class data frame, and then a variable number of extra arguments, and it returns an array of integers. And you can see the other signatures in this slide. When you see a signature that has the type any in it, this is likely a point where we're losing precision and where a richer type system would have allowed us to give a more accurate type signature. But, looking at this, I can say that these types are definitely better than not having any type information. So it's certainly an improvement, and a lot of them are quite actually accurate. So the next step was to figure out how good these type signatures are. And here the metric of goodness is as follows, and I need to explain a little bit what we did for you to understand it. So the type signatures that I showed are not sound. By that I mean they may be wrong. How do we obtain those type signatures? Well, we have this pipeline. We start with the whole of the CRAN repository, and it's at the time 15,000 packages. We picked out of those the 400 packages that were the most widely used and had the best code coverage in their tests. And then for each of these packages, we ran all of their tests, all of the vignettes, all of the examples that were packaged with it. And this allowed us to observe how functions were called. And from each call of these functions, we had individual signatures. And for the same function, from a list of signatures, we synthesized a single type signature. And this is what I showed you in the previous slide. So then the next step we had was evaluate how good these type signatures are. So what we did is we took our type signatures and we instrumented the library code. For each function in the library, we added a contract that checked, are the types that are coming in as arguments are the values that are coming in as arguments of the expected types, and is the result of the expected type. Now we had these rewritten libraries. We took a look at CRAN and we found all the packages that transitively used our 400 libraries. There's 8,000 of them. And we took all of their tests, all of their examples of vignettes. That we could run. And what we did is we observed, running this client code, how often type signatures did not match with the actual arguments. And the result is we recorded 98 million contract tests, and about 2% failed. Another way to say it is our signatures were accurate 98% of the time, which is, it's definitely good as a starting point. And the way we see this tool being used is we get initial inference by dynamic analysis, and then developers refine the types using their domain knowledge. But most of the hard work is already done by the tool, so hopefully the changes they have to make are small. All right, so the third problem that I want to talk about is one of performance. And the issue here is there's a perception that R is slow, and regardless of truth, people will write code in C rather than in R and link it to the R executable. And the more C code there is, the more likelihood for bugs there is, and the harder it is to evolve the ecosystem, because you have a lot of hidden invariants that are lurking in that C code. Here on this slide I have a graph that is a few years old, but basically what it shows is an experiment where we compared the performance of C, Python, and R on a set of computational benchmarks. Python is about 50 times slower than C, and R was about 500 times slower than C. Take this with much salt, but the point is, and this is still true today, that it is very easy to write an R program that will be slow, and that will be very slow. Why is that? Well, it feels like R was designed as a challenge to compiler writers. It's an adversarial language. Consider, it's this function. It's a function named f, who takes an argument b, and it couldn't be a simpler function. It just adds b to itself. Easy and peasy. Here's a call of f. Call it, and I pass whatever bad returns. Now the problem here, of course, is that since it's a lazy language for now, we actually don't evaluate bad at the call site. We will only evaluate bad when we're running f, when we touch the first b. And for the second, we don't need to evaluate it because we remember the result. What could be a definition of bad? Well, what about this? A function that goes up one in the call stack, looks for the symbol b, and deletes it. What this does is it's going to delete a local variable of f while f is running. And then the second time we try to access b, it will not be found. So what is a compiler to do with this? It's hard. So we are working on a system called Je, which is a just-in-time compiler. That's a drop-in replacement for the R bytecode interpreter. And in Je, we are doing some exciting compiler research. We're pushing on the notion of speculation. So what we want to do is make the bet that what I showed you before never happens. And as long as our bet holds, as long as this assumption remains true, we can generate efficient code. If at any time, the assumption it doesn't hold, then we have to throw away the efficient code that we have compiled, jump to a slow but correct version of the same code, and proceed from there. So this is speculation. It's done in most just-in-time compilers for languages like JavaScript. So what we've done that is unique is that we've explicited all the instructions that are needed for this process of making assumptions about potential invariants and then de-optimizing the code if the assumption doesn't hold into the intermediate representation. So we have 4 instructions: checkpoint, assume, frame state, and deopt, that are specific to this speculation process. And what we then did is we showed a proof that some optimizations are correct in the presence of these assumptions, and we also mechanized that proof and so in Coq. So we have got assurance that this approach is sound. And we also have a compiler written in C++ that targets LLVM that uses this approach. And now we're trying to push the notion of speculation as far as it can go. All right, so I will conclude. I've told you that data science, as its practice, is an act of programming. Just like any act of programming, it will be subject to errors. And the work programming language, software engineering researchers do is directly applicable to data science if we choose to try to keep all of the investment that people have poured into existing infrastructure and improve them. And this is what we're doing in the LA project. We're evolving language ecosystems. Thank you for your attention. I welcome any questions, by any means. Thanks a lot.